Okay, great. Welcome back, everybody, to this week's Infosys Chandrasekharan Random Geometry Colloquium. Today, we're extremely glad to have Manan, although he's at MIT right now, but he's spending time at IIS. We'll be giving a talk on atypical stores on a directed landscape geodesic. Over to you, Manan.
Thanks for introducing me and for inviting me to give this talk. Very happy to be here. So I'll be talking about this work, which I completed quite recently, about 3 to 4 months ago, and it's on atypical stars on a directed landscape geodesic. So the directed landscape, it's a model of random geometry. And it was introduced quite recently, actually. It was introduced in 2018 by Dauvergne-Ortmann-Virág. So, I mean, the model is a continuum model, but it's a bit difficult to introduce in the continuum. So I'll first tell you about some discrete stuff, and then because actually there's a lot of models which are expected to converge to this directed landscape. There are models in this Ganguly-Zhang universality class, which is usually known as KPZ. So yeah, I'll start telling you with some discrete model, and then we'll rather quickly go into the continuum. Okay. So which model am I talking about? I'll talk about last passage percolation. And in specific, I'll talk about exponential last passage percolation. So I guess most of you have probably heard about first passage percolation, but for last passage percolation, in particular exponential last passage percolation, there are some magical bijections which actually allow you to get a handle on the scaling limit. So that's why we talk about this. Okay. So what's the model? It's this. You just start with a lattice Z2. Okay. And now for every point U on Z2, you associate a random variable XU. And this random variable is exponential 1. And you want all these random variables to be IID across all these lattice points. Okay. So you have this field of random variables, and now what you want to do is you want to define lengths. I mean, you finally want to get a geometry, right? So we will define lengths, but first I want to tell you that it's a directed model. So you only measure lengths between ordered points. So I say that points U and V are ordered if U is less than or equal to V. By that I mean coordinate wise. So that means that V is to the up and right of U. Okay, so this is the ordering, and now I define the length of path. So if I have a path gamma going from U to V, so again this path gamma must be ordered. And what do I mean by that? Again, it should only take up and right steps. So I'll draw a path. You can measure the length of such a path. It's a path which goes to the up and right. Okay, if you have a path like this, you define its length, L of gamma, to just be the sum of the vertices it goes through. Okay, so I'll use W because I already used U and V, and W is in gamma. This is the length
so
of
variables are attached to the vertices, not the edges, right? Here?
Yeah, they're on the vertices, yeah.
Okay.
Mm-hmm. That does not actually, I think, turn out to matter, but here we do it in the vertices, yeah. Okay, so I defined the lengths, right? And now I want to define the distances. So here it's traditional to call the distances as passage times, and I define the passage time from U to V to be the largest such length. Right. I mean, usually when you think of distances, you take to be the minimum such length, but here we do the largest because it's these models are last passage percolation models, so it's traditional to do the largest one. So that tradition has stuck on. Right. So you do the largest length, and then you can define the geodesic, which is say gamma, capital gamma from U to V. It's the path attaining this length. Right. So yeah, I mean, you can think of this as a model of random geometry. And so usual metrics satisfy the triangle inequality, and this satisfies the reverse triangle inequality because, I mean, say this was the point W, I mean, because you took the maximum instead of the minimum, right? So the reverse triangle inequality would say that the passage time from U to V, that is at least the passage time from U to W plus the passage time from W to V. These sort of things you can directly see from the definitions, right? Okay, so we have a random geometry model and I define geodesics. And okay, another thing I should say is that almost surely every 2 points have a unique geodesic between them. That's actually not difficult to see because the exponential distribution does not have any atoms. So this is a true thing that almost surely gamma UV is unique.
Manan, so geodesic means longest path, right?
Yeah, it's the longest path, right? Okay, so right. So I told you about the model. Now we want to talk about the scaling limit, right? So I mean, you have this random model on this random geometry on Z2, and you want to look at large scale behavior. You want to look at what kind of long range structure emerges when you take points U and V far away, and you look at the geodesic between them. So what's the kind of structure there? So for that, I need to first tell you what scaling you have to take, and that is the KPZ scaling. So I just write KPZ 1, 2, 3 scaling. Right. So yeah. So okay, you have your lattice. So usually we work in the upper right quadrant. You take a point 0, 0, and you take a point n, n. And let's draw the geodesic between these 2 points. This is the diagonal line. So you have some path, unique path. So now what happens is that this length, this transversal length with the geodesic fluctuates on, that length is of the order n to the 2/3. Right? So this is the true part of the KPZ 2/3 scaling. And this thing, I mean, as you can of course see, is length n. Right. So yeah, I mean, whenever we take a scaling limit, we will have to respect these sort of exponents because you want your final geodesic to be an order 1 object, right? Okay. And now another thing, so I want to look at the scaling limits of passage times themselves. So for that, first we change our coordinate system because yeah, that makes it more convenient. So
what is the evidence that leads you to do KPZ scaling for this particular LPP model? I mean, is there some theorem which is known that the variance in the transverse direction is n to the 2/3?
Yeah, that is true. So for exponential last passage percolation, there's a magic bijection, this RSK bijection, so which actually transport you to some random matrices and things like that. And there you can explicitly compute the variance. So the fluctuation scale comes out to be n to the 1/3 of the passage time. So these things are not known if you don't have integrable models. If you have some model where it's not exponential, then these things are not known and you're left completely in the dark. But for these specific models, you actually know quite a lot. Yeah. So sorry that I'm not citing many results, but yeah, these are the things that are known, and yeah, I can tell you later about sources if you want. Yeah. Okay. Right. So I was talking about the change in coordinate system. So instead of the quadrant, we usually work with, we just tilt it 45 degrees, and yeah, we think of this direction as the x direction and this direction as the time direction. So going from 0, 0 to n, n would mean going up in the time direction. Okay. And earlier I had defined the passage time u, v. So we now write it in terms of these coordinates. It's just xs. You just write passage times like this, and the directedness would mean s less than equal to t. Okay. Right. So what's the directed landscape? You have to first respect the KPZ scaling. So you have to take n to the 2/3 x ns, right? This is, as you can see in the left figure, geodesics were doing like this, so you need to respect it. So, and the first order behavior is actually, it's 4n times t minus s. This comes from the integrability. And then there's a fluctuation term, which is n to the 1/3. And then there's a continuum field. Okay, I should not write equal to because all this happens as n goes to infinity. Xs yt. I'm not writing a proper statement, but a proper statement is something like, okay, for each n you have this LPP model, and you can couple all these models in a certain way such that as n goes to infinity, this passage time t, this passage time which I wrote here, this thing converges after removing this covariant times t minus n term and dividing by into the 1/3. This thing converges in the locally uniform topology or something like that to a random 4-parameter function, which is called the directed landscape.
So like, simultaneously over any compact set.
Yes, exactly. Yeah,
Okay.
for any compact set, uniformly on that, right? Okay, so this is the directed landscape. And yeah, so as I told you, it's a lot of integrability is used. So I'll tell you some aspects of the integrability. They might not be used later, but just to familiarize you with some things like how certain arguments go. So what things are known for the directed landscape, right? Actually, a lot is known, and there's some very explicit integrable things. So suppose I took the timeline 0, okay, and this is a timeline 1. This is, and then I take a space point here 0, and a space point here x. Okay, and I consider the passage time L 0 0 x comma 1. So how does this look like? And the answer to this is that this is an Airy-2 process, parabolic Airy-2 process. So you should think of it as a stationary process minus a parabola x square. So like it. And this is called Airy-2. This is some process coming from random matrix theory, and this process is actually locally Brownian, which is an important thing. As in the sense that if you take any interval and you restrict the process there, you measure its derivative, radon-equivalent derivative with respect to Brownian motion, then you can actually show it's an LP for all P. So it's very strongly Brownian.
One small thing, Manan. So instead of taking this, let's say this pi/4 direction, if I took other direction, it would be same, or what?
Yeah, that is true. So in any fixed direction, which is macroscopically away from this x and y axis, this you'll get a directed landscape. So yeah, I should have mentioned that. But that's
okay.
true. Yeah.
Okay.
The mean term will be different. It won't be 4n. It will be something else.
Okay.
But you'll get the directed landscape. Yeah.
Okay. Thank you.
Right. Okay. So this distance profile, you go from 0 to x. This distance profile looks locally Brownian. It's an Airy-2 process. And actually, there is even more integrability. So instead of looking at the best path, looking at the passage time from 0 to x comma 1, we can do something more. What's this? Again, I do the same thing. I go from 0 and I go to x. But now instead of measuring the passage time, I measure this different statistic. So I measure the best length of k disjoint path. So this will be a function of x, right? So earlier I was just taking k equal to 1, so it was a geodesic, but now there will be some k disjoint paths, which, yeah. So this thing actually has also a very integrable representation. So what happens is that there's this object called airy line ensemble, which again comes up in random matrices. And so what is it? It's an infinite collection of lines. It's like the first line is called, we call it P1, P2, P3. They're all ordered, so they're non-intersecting. They're all Brownian. And if you compute this quantity, best length of k disjoint paths, this is summation of pi of x from I equal to 1 to k, the top k line sum. Right, so I just want to tell you that there's a very integrable representation for this sort of quantities. If you just want the best length, then you just sum up the top k lines, and you'll get the best length of k disjoint paths.
So you just look at the top k lines in terms of the length, basically.
Yeah, if I want the length of the best k disjoint paths, there's this integrable object, airy line ensemble. I just sum up its top k line. So this will be this. Yeah.
The top line being the geodesic, and then the next ones are right.
Exactly. So this top line is the line itself is not the geodesic, but the top line tells you the geodesic weight. So it tells you the passage time as x is varied.
Okay, so sorry, then I can understand. So yeah, again, so what is the definition of this object? Yeah.
Of airy line ensemble?
Yeah. No.
Maybe I won't tell the definition.
No. That is okay. So this best length, so like best length of k disjoint paths. So what is this? What do you exactly mean by this?
Okay, so you take right. So this is yeah. Sorry about that. So I should tell you that we can define lengths in the directed landscape, right? Yeah, right. So yeah, just as we define lengths in last passage percolation, we can also define lengths in the directed landscape, and I'll quickly write that. So okay, if you have a path, say gamma, from S to T to R, right? And say gamma of S is equal to X and gamma of T is equal to Y. It's a path going from X to Y. And if I want to define its length, you can define it. And what you do is you consider all subdivisions. So yeah, so you do L of gamma Si, comma Si, and then Si plus 1, sorry, gamma Si plus 1, Si, right, the usual sort of way. And you minimize this over all subdivisions. So this defines the length, and then you take the geodesic is the path which maximizes this length. So yeah, so I should have mentioned this before, but you can define lengths and then you can get geodesics, right? And now I'm saying that the length of the k best disjoint path. So if you took you just maximized over the set of k paths which are disjoint, then you'll get this integrable thing. So this is not really needed for what we're talking about later, but I just wanted to tell you what kind of integrability there is. Right. Okay. So yeah, we define geodesics in the landscape. Okay, I'll not say how to represent them. Geodesics. I just again write it as gamma u comma v. Sorry, not u comma v. I'll write this right here. Right. Okay. And what else should I say? I should tell you another important property, that the landscape is regularity. So I should, yeah, the landscape, it is Holder continuous with 1/2 minus in space. And Holder 1/3 minus in time. So actually the first point, the first Holder continuity you can directly see, and that's why. So why is because, I mean, I told you this thing, right? I told you it's an airy process and it's locally Brownian. So of course, Brownian motion is 1/2 minus Holder. So yeah, but the different thing I'm saying that is that if I went in time direction, then you'll get Holder 1/3 minus, yeah. Okay, so yeah, this is all the preliminary stuff. So now we can move on to the fractal geometry part. Right. So to talk about this, first I'll quickly tell you about coalescence. So coalescence is a thing which is very common to random geometry. Actually, it happens in last passage, it happens in directed landscape, and it also happens in these other models like LQG and Brownian maps. So it's a very common thing to random geometry. And what is it? So okay, so say I take 2 points. There's 2 points, P1, P2. P1 and P2 are quite close to each other. Okay. Then I take 2 other points, Q1, Q2. They're also very close to each other, but the pair P1, P2 and Q1, Q2, they are quite far apart. And now I look at the geodesics from P1 to Q1. So if it were usual equivalent geometry, and then I drew the geodesic from P2 to Q2, then it would stay completely disjoint. But in random geometry, this does not happen. What happens is that the geodesic from P2 to Q2, it goes and merges with the geodesic from P1 to Q1, stays with it for a bit of time, and then it goes to its destination. Yeah, so this happens in random geometry, the intuition being that, okay, there's lots of randomness in the space. There are certain regions which turn out to be extremely good, very attractive for you, and everyone tries to go there, right? So this is the phenomenon of coalescence, which happens in the directed landscape also. So, and this actually leads to the emergence of some fractal structure. And I'll talk about that now. So, right, so there are 2 situations.
What what is the quantitative version of this? I mean, how close does it have, do P1, P2, Q1, Q2 have to be? One. Second,
Right.
depending on that length, I mean, how large does the separation between P1, P2 and Q1, Q2 have to be? And what is approximately the length between, I mean, of the stuff that they have, I mean, of the path that they have coalesced together? So, I mean, this is a
Okay.
thing you've done, right?
So say if you're in LPP, right? I think maybe it's easiest in LPP. And I had 2 points like this, and they had a separation of little of n to the 2/3. I had and say these were going to 2 points here. This was n.
I see. Okay.
And so you expect it to be on scale. So if this was actually n to the 2/3, then you would say that, oh, the probability of coalescence is constant. You see. And this length is also of order n.
I see.
It's like a, yeah.
And so here's I mean, okay, so yes, I understand it's of order n, but that length divided by n as n tends to infinity, does it converge to some number in LPP?
Yes. So it will converge. I mean, yeah, it should converge to this length in the directed landscape when you. So the LPP models are being coupled so that they converge jointly to the directed landscape, right? And then there will be this length of this in middle portion in the directed landscape, and I would say that it should converge to that.
Okay. Fine.
Okay. So yeah, there are two situations. So because of this coalescence, so say I took a point, okay, point Q, and I took 2 points again, P1, P2. In the typical scenario, you would expect that if I drew a geodesic from P1 to Q and from Q to P2, they have this initial segment in common. That's what will happen actually that's what will happen for almost every point Q. So what am I saying? I'm saying that so almost surely for almost every Q, if I took any geodesics P1, P2, these geodesics, okay, maybe I'll write gamma Q, comma P1 and gamma Q, comma P2, they share an initial segment. Okay, so if this happens, then I call Q a forward 1 star. I mean, call it a 1 star because there's only one geodesic arm coming out from it locally, right? But there's another situation, which is that you can find 2 points P1 and P2. You have got a point Q, and then you found 2 points P1 and P2, so that these geodesics are disjoint apart from the point Q itself. Okay, and in this situation, we call it an atypical star.
Just so that I'm a bit comfortable with the qualifiers, Manan. So you're good. There's non-exceptional points, like I mean, this which is a typical point, which is the forward. Is that so? With probability on any point, it is true that no matter where you take any 2 points P1 and P2, they will coalesce, right? That's
right. That's true.
For all pairs of points, basically.
Yeah, so the coalescence segment will become very small if you take 2 points P1 and P2 very far away.
Of course. Yeah.
But yeah, okay. It's true that they will coalesce. Yeah.
And the exceptional point is that there exists some 2 points for which you'll have they are disjoint to disjoint arrays. Okay. Okay.
Okay. So. Yeah, so I mean, here I said a forward 1 star, but you can also define, of course, reverse 1 stars, right? But I mean, you can do the same thing in the backward direction. But so I will just say that Q is a 1 star if both forward and reverse 1 star. So almost every point will be a 1 star. This is the usual scenario. And else it is a atypical star. Okay. Right. So now this is a, I mean, you can actually show that it's not very difficult to see that such points need to exist. Even though they are measure 0, you can see by certain reasons due to planarity, because I mean geodesics cannot cross and things like that. So these points must exist, right? Of course, if geodesics are coalescing, then these points are atypical stars, these sort of points, just by definition. These are not a typical atypical star, but these are atypical stars. Okay. Right. So now what kind of stuff is known about the fractal properties of this? So I'll tell you the first result, which is this. So suppose you take a horizontal line and you start looking at all the set of all the atypical stars which are there. Okay. So basically you consider atypical stars intersected with horizontal line. So the result is that the Hausdorff dimension of these atypical stars, this is equal to 1/2 almost surely. And this was shown by this was shown in the first by Basu, Ganguly, and Hegde, and then there were subsequent works which improved the result. So yeah, the other works were one was by Bates, Ganguly, Hegde, and then there was by Ganguly and Hegde, and then there was a final work by Dauvergne. Yeah. Okay, so is one thing. Okay, so they did not actually formulate the result in terms of stars or anything like that. They actually just looked at points which have disjoint geodesics to 2 fixed points. But I formulate the result like this here because it's more relevant to what we will state later. This was the first result which I told you, and now there's another result where instead of a horizontal line, you now took a vertical line. And again, you looked at the star points on the vertical line. And the result is that the dimension of these star points, the Hausdorff dimension, which is actually equal to 2/3 almost sure. So later I will actually tell you how, I mean, I'll give you some partial proofs of some of these numbers, not all these numbers, but I'm just telling you some results right now. And this was by Ganguly and Zhang. Okay, and then there's a very recent work by Duncan Dauvergne. So where what he actually does is he considers K stars. So we said 1 stars, right? 1 stars have only 1 arm, and then atypical stars, which usually are 2 stars because that's the least amount of constraint. But you can consider 3 stars. What happens if there are 3 geodesics, 4 geodesics? So he said that the dimension of 3 stars. So he considered some different dimension actually. So he computed in some different sense it's 2, but it's not the usual one. That's why I just thought
it's if I remember, it's a different metric, right? I think
it's a different metric.
Yeah,
Exactly. So, but yeah, what we can see is that he also showed that there are no 4 stars. I mean, this is independent of the metric. So, sorry. Oh, I should say another thing. So Ganguly and Zhang, they also showed that the dimension of atypical stars, this is equal to 5/3, the planar dimension for R2 dimension. And this was by Dauvergne. Okay. Right, so we'll continue on this theme, but so we now come to the result, which is the subject of this talk. So okay, so what we do is we want to instead look at the fractal geometry on a geodesic. So yeah, so I mean, this is like a horizontal line, this is a vertical line. These are all still typical regions of the space, right? So you want to compare how many stars there are on a geodesic, how many atypical stars, to how many stars there are in a typical region, right? So what do? We take a geodesic between say 0.00 and 11, not 11, but 0.1. Okay, take a geodesic. I'm almost showing a unique path. And now we look at this atypical star on this. So you get something like this, right? You want to find out how many of these there are. So now I state the result. Okay, so consider the set of times t. Such that if I look at this geodesic, I just call it gamma. Gamma t comma t is an atypical star. Then the dimension of this set is equal to 1/3 almost surely. Yeah, so we just want to compare with this result by Ganguly and Zhang, where they say that on a vertical line, the dimension is 2/3. But here we are saying that, okay, if instead of a vertical line, you took a geodesic, then the dimension drops down and it's 1/3 now. So you expect, so in this sort of, in this sense of exceptional behavior, there are less exceptional points on a geodesic than of a geodesic, a typical region. Right. Okay, so now I go and start talking about some of the proof techniques. And so first what I'll do is I'll talk about the lower bound, and I'll talk about the lower bound for the topmost situation, the situation of a horizontal line, because those techniques are actually quite relevant for this proof also. And then, yeah, we'll go to the lower bound for this.
By the way, Manan, before we go to the more quantitative version, I'm just saying that, let's say one is interested, like very like the kind of a 0-1 law type, like that. Okay, if I want to say that the Hausdorff dimension of this quantity is almost surely constant, is there a way to say that easily without getting into, let's say, all the nitty-gritty analysis? Like, is there a way to say without actually computing it that the, like, I'm just like in the sense of this thing, UN proved, geodesic dimension that in Liouville quantum gravity. So he has this paper when basically proves that using coalescence that it's almost surely constant. We don't know what the constant is, but yeah. So, but is there a way that it is probably relatively simpler to be, or no? Probably you have to go through this way. Just a curiosity.
Might be. I mean, the way I would think it would be similar to UN's thing that instead of doing finite geodesic, you first go to an infinite geodesic, and then you want to show that the sigma algebra around 0 is trivial.
Okay,
right?
okay. Like this, this kind of okay. So this kind of like somehow obtaining some ideas of like this Blumenthal kind of thing that you usually do in the classical cases. Okay,
Yeah.
fine.
So even thing actually, he does show that the geodesic has a dimension, but he does not say that all parts of the geodesic have the same dimensions, right? So I guess here you can still get a 0-1 law by zooming in around 0, and then it starts looking infinite geodesic.
That's right. Okay, fine. Yeah, thanks.
Okay, yeah. So I'll go to the lower bound. And lower bound for the 1/2 lower bound for this question, right? This dimension. Okay, so the way this lower bound proof goes is by constructing this quite interesting object called a difference profile. So, okay, I'll now tell you about this object. So, again, you start with 2 timelines, 0 and 1. You take a point 0 here, and you take a point 1 here also, space point 1, and you have a point x here. Okay, so I define the difference profile, d of x, to be the difference of passage times. So this seemingly simple object actually encodes a lot of information. And the most interesting property is actually that, so if x, 1 Okay. So okay, what do I want to say? I want to say that if x had the property that if x did not admit disjoint geodesics to 0, 1, if x does not admit if the situation is a typical situation, then in fact this difference profile is locally constant in a neighborhood of x. And why does that happen? That actually happens because of coalescence. So I'll tell you why. And okay, so this is the point where these geodesics meet, and say the length of this path is A and the length of this path is B. Then you can of course write that d of x is A minus B, right? Because other part is common. And now I took a point x prime here, very close to x. Okay, I drew the geodesic from it to 0 and to 1. So what will happen by coalescence is that it will merge, right? And then I compute d of x prime. Again, the common parts actually cancel out. So it's again A minus B. This is the reasoning behind this, and that's why you expect it to be locally constant around x. So, but you can actually show that d of x is not globally constant. That's something which is not difficult to show. Right. So what does this tell us? And we also know that d is locally Holder 1/2 minus. I'll just write, because I told you that the directed landscape itself is Holder 1/2 minus in space, and I'm just subtracting two landscape values. So now what I want to say is that this directly implies that the dimension of the set, dimension of x, is that d of x, d is not locally constant around x, not constant around x. This dimension should be at least 1/2. Okay, I'll just quickly say why is that. So suppose that was not the case, so you could cover this set. I mean, intuitively you could cover this set by okay. If not, then cover by epsilon to the minus 1/2 minus delta many balls of side radius epsilon. Right? So this you cover this non-constancy set. Everywhere else it's constant. And in each ball you use the Holder continuity. So in each ball you can change by at most epsilon to the 1/2. There'll be some plus delta or something also, but I just put epsilon to the 1/2, and you have okay, sorry, actually this will be plus. And it becomes epsilon to the delta. But you know that your distance, I mean difference profile is not globally constant. And this will go to 0. Right. So if you could cover it by such little balls, then difference profile cannot change at all. Okay, so this tells you that you have a lower bound of 1/2. And of course, if you have a lower bound of 1/2 on the set of points with disjoint geodesics to 0 and 1, you of course have a lower bound on atypical stars, because in particular, I mean, these are atypical stars. Right. Okay, so this difference profile, it works here, but I should tell you why it works here. It seems very, very magical. The intuitive reason for it working is that here the difference profile turns out to be monotonic. And so what do I mean by that? I basically mean that the usual sense, d of x is bigger than d of y.
So by the way, Manan, so just a small thing. So, I mean, in order to prove that, like, okay, so as was said in the beginning, that the directed landscape itself in the space coordinate is Holder 1/2. But here actually we're considering the difference, right? So that could be smoother, but so that also needs to be shown, right? That the difference is also, this difference profile is also Holder half, exactly, right?
But if each individual function is Holder half, then the
no, but
difference should
isn't it, no,
also
okay, what I'm just saying, because you're obtaining a lower bound on the Hausdorff dimension, right? So
yeah, if you're saying it might not be tight, is what you're saying, right?
exactly, because here actually don't you need that it is not better than that, so something like that. So that's all I'm saying. Of course, as you
So
said,
right now I'm just doing the lower bound. For the lower bound, this is enough, but you are right in that difference profiles might not always give you the correct upper bound also. Right? It's possible that the upper bound is, and I'll actually give an example where difference profile fails and it does not give the correct upper bound. But I think for the lower bound, this is, yeah, you do get a lower bound. It's another question if the lower bound is tight or not.
Okay. Okay.
So I'm just now telling you some intuition about why you expect the, like, why would one expect this lower bound to actually be tight? And the intuition is that the difference profile turns out to be monotonic in the sense that, yeah, if you had points x here, y here, then the difference profile at x is bigger than the difference profile at y. So this is a simple proof. I'll not give it here, but I'll give a related proof in a few minutes. So that will be more closer to our situation. But so the heuristic here is that the difference profile sort of gives you, I mean, the difference profile is only changing at these exceptional points. So, and if it's increasing monotonically, there are no cancellations happening. You expect that, okay, there's some Hausdorff measure of these atypical points, which is like the, so I mean, dx minus d of y gives me the Hausdorff measure of these atypical points between x and y. But if there are some cancellations happening, then you would not be able to track that Hausdorff measure just by this entire difference dx minus dy. You would have to do some variation or something like that to get the measure. That's sort of intuitive thing. But so I'm just saying that if the difference profile is monotonic, then you might expect, okay, probably this thing is tight. Let's try to show that. So the upper bound here, which Basu, Ganguly, and Hammond did, that proceeded by a different proof, which I won't go into now. Now I come to our setting where we are doing atypical stars on a geodesic, right? Okay, so first, actually, I should give a caution that difference profiles don't always work. And I'll give you an example. So this is this vertical line question, which was solved by Ganguly and Zhang. So this dimension is 2/3. And now if you try to do it by a difference profile argument, you might do something like this. You might take this point -1. You might take this point 1, and you might say, okay, I consider the difference profile S maps to L10 0S minus L minus 10 0S. Again, you can actually show that the difference profile will only be constant around points which do not admit disjoint geodesics to -1 and 1. You can do the same thing actually, and everything goes through, but you now use the 1/3 minus Holder continuity of the landscape in time. And if you do that, you actually get a lower bound of 1/3 if you do all the calculations. But that does not turn out to be the correct answer of 2/3, even though of course 2/3 bigger than 1/3. But this time it fails. And the difference profile here actually, it turns out it is not monotonic. So yeah, this was a situation where difference profile fails. But now we come to our situation, which is this geodesic stuff, right? So what happens there? So I make a geodesic between 0.00 and 0.1, and we look at the. I want to define a difference profile. So this time I call it d dot. Say. So what's the difference profile? I just define d dot s. Yeah. To be okay, I take this point 1 here. D dot s is L10 gamma s minus L 00 gamma s. This is the difference profile which we define here, and you can again do the same thing and say, okay, if there was a point which did not admit disjoint geodesics to these 2 points, 0 and 1, then difference profile is locally constant around that point. So in particular, I can get a lower bound on the dimension of the set of points which admit disjoint geodesics. Right. So if you do that, you get the dimension of non-constancy. This actually you get, this is one, is at least 1/3. You again use the Holder 1/3 minus property of the landscape in time. But this time, this difference profile actually turns out to be monotonic, which I'll show now. And this is why you might expect, okay, this is probably tight, and we can think about how to show it. So the lower bound proof here is actually much simpler than the upper bound proof. But yeah, telling you the lower bound proof first. So we'll now talk about the monotonicity. I'll give a proof. It's really simple. Monotonicity of the difference profile. So what do I want to say? I want to say d dot of S is at least d dot of T if S is bigger than T. And just recall the expression. You are subtracting the distance from 1 minus subtracting minus the distance from 0. Okay. So let's do the computation. Draw the geodesic again. I have a point S. Sorry, S was above, I think. Yeah. And a point S. So what's the thing on the left? It is L10 and gamma S, right? And I have to subtract L00. Sorry, yeah.
Sorry, by the way, Manan, is it wrong or naive to think of this difference profile because it reminds one of this Boseman functions a bit in a certain way? Or
Boseman functions are like the distances from infinity, right? So I think
yeah, okay, yeah,
it's not the same.
No, it's not. Yeah,
yeah. In Boseman functions, yeah, you're right that you do have to center, but that's because you just want to make it order 1. Right?
Okay. Yeah. Okay.
Yeah. Okay, so you want to show this is bigger than. Wait. No. Okay. Right. Okay. So what do? We take this term, we send it to the right hand side, and we use that this gamma is actually a geodesic. So if you send it to the right hand side, what you will get is L gamma T, comma T. This to gamma SS, because that thing is a geodesic, and now you just need to show this. Okay, you just have to show this. And this is just by the reverse triangle inequality thing which I was saying. So I mean, what this is saying is that if you want to measure the passage time from 1 to gamma S, that passage time is better than going from 1 to T plus taking the geodesic from T to S. That is, of course, true, because the left-hand side is the maximum over a larger collection of paths. So yeah, this is the proof of the monotonicity. Okay, so if you do this, I mean, yeah, this gives you a heuristic of why the thing should be tight. And now I'll start in the last 10 minutes. I'll just say some things about the upper bound. Okay, and this will be quite quick, and I won't give a proper proof. Actually, maybe I'll just go to the next page. So what kind of things do you need? What kind of estimate do you need for the upper bound? So I'll quickly first tell you about the 1/2 situation, the horizontal line situation. Right. So what you need to control is you need to control the probability that the difference profile, which I had defined there by D. So yeah, the difference profile, the probability that this thing is not constant in an interval. A plus epsilon. Say if you can get a good estimate for this. Sorry. Yeah, if you could show that, say, this thing is this probability is epsilon to the half, right? So yeah, recall that what we were doing is we had 2 points here, 0 and 1, and we were considering the difference profile from here to this point. So okay, so I mean, we want to finally bound a dimension of atypical stars, but you can do some countable union argument if you are able to just get the dimension of points with disjoint geodesics to 0 and 1. So in the end, you only need to do points with disjoint geodesics to fixed points. So I'm saying that if you had such an estimate, that if I had an interval A and A plus epsilon, and I could find out, okay, what's the probability at the difference profile D? It's not completely constant on this interval. If I had this is epsilon to the 1/2, then I could cover it by epsilon to the cover space by epsilon to the -1 many balls, and then I'll do multiply this by epsilon to the half, and I'll get epsilon -1/2. The usual sort of technique for dimension of a bound. So this is the sort of estimate that you need to get in this setting, the horizontal line setting. And now I'll talk about the R setting. So what do we do here? I'll draw quite a big geodesic. So what we do now is we cover time by delta size boxes. Okay. We do put delta boxes like this, and the KPG scaling you have to respect it. It forces us to put delta to 2/3 in the space direction. So I have delta to the -1 many boxes, and here I have 2 points, 0 and a 0.1, right? I'm looking at points on the geodesic which admit disjoint geodesics to these 2 points. Okay. Suppose this point, there was a point in this box, say, which admitted disjoint geodesics, which had 2 disjoint geodesics like this. Right. Suppose the setting was like this, and now I zoom in a bit here. So I have this thing, and there are 2 geodesics going like this. So now what you can do is you can create a proxy point in between, which actually has 2 disjoint geodesics to 0 and 1. So what does this is that initially your point was random. The point which had 2 disjoint geodesics, it was somewhere random in this box, but you forced it to stay in this horizontal line, which is a deterministic line. So yeah, for some notation, say this box is BI, and this timeline is TI. Okay, and this line segment. This line segment is actually, I call it LI. Okay. So now what I'm saying is you need an estimate like the probability that the difference profile, and now which difference profile. So I'll write a TI at the top. If I considered the points 0 and 1, and I took the difference profile to this horizontal line at time TI. So I am fixing 0 and 1, and I'm bearing my spatial point on this horizontal line at time TI, and I'm just looking at the difference profile. I want to bound the probability that this difference profile is not constant in this interval. Is not constant in an interval Li. And the length of the interval Li is actually delta to the 2/3. Right. So I want to do this sort of estimate. So now what's the difference between the above estimate and this estimate? I'll just talk about that. So in the above estimate, you actually have 2.0 and 1, and you are asking for the non-constancy of the difference profile in a fixed interval. But the only difference here is that this interval here is random, and this interval here actually lies on a geodesic itself. So these are the 2 distinctions between the 2 situations, right? The above probability is for a fixed interval, and this probability is for a random interval. So to be able to do this, you need to have some understanding of the environment around a geodesic. And that's the core thing which actually goes in. I mean, you don't know the full environment, you actually only need to know the you need to know how the passage times from zero are how they behave in around the geodesic. So in the last 5 minutes, in the last 4 minutes or something, I'll just say some things about the. I'll not go into the full proof, but I'll just say things about geodesic versus off geodesic. So there's a very specific thing which happens on a geodesic.
I mean, feel free to take 2 minutes extra. That's fine.
Okay.
Yeah, no, right.
Right.
This is interesting stuff. So, anyways, yeah.
Yeah, so I want to talk about this environment around the geodesic stuff. So, right. So, what is a geodesic, right? I mean, you're just looking at the best path. So, again, a geodesic. And suppose I was looking at the timeline path, right? And I want to say, okay, I find the point where the geodesic hits here. So, what is that point exactly? To find that point, I have to do this, right? I just have to find the argmax in X. I have to find the argmax of L 0, comma X half plus L X comma half comma 0, 1, right? I want to find the point which maximizes this. That's of course the point on the geodesic. But I told you earlier the distance profile. Each of these distance profiles, these behave as airy process, right? It's a specific process, locally Brownian in particular. Okay, so you have two airy processes which are actually independent. You sum them up and you find the location of the maximum. They're locally Brownian, so we just replace them by Brownian motion for now. So you have two Brownian motions. Actually, I forgot to tell earlier, but the diffusivity of the Brownian motion is 2 in this airy process if we look at. So you have two Brownian motions, square root 2b1 and square root 2b2. What you are doing is you are doing square root 2b1 plus square root 2b2, right? And then you want to look at the maximizer of this and say, the question is behavior of b1 or behavior of square root 2b1 around the argmax of square root 2b1 plus square root 2b2x. You take the argmax of this and how does square root 2b1 behave? So actually this stuff, yeah, this environment around geodesic stuff was done in a few works by James Martin, Alan Sly, Ganguly-Zhang, and then there was a paper by Dauvergne-Ortmann-Virág. So yeah. So I'll just do I'll do a quick computation. So you want to compute this, right? How does square root b1 look like around this argmax? So we write square root 2b1. We write it as square root 2b1 plus square root 2b2 plus square root 2b1 minus square root 2b2. And I think you have to put a 1/2, right? So we know that if you look at a Brownian motion, so first of all, this term is independent of the square root 2b1 plus square root 2b2 part, right? It's Brownian motion stuff. And if I condition, if I look around the maximum of a Brownian motion, then what I see is a 3D Bessel process, which I denote as R. So I see a negative 3D Bessel process. So what happens is that around the maximum, you have 1/2 times, the diffusivity, to look at the diffusivity property is 2, right? Minus 2R, which is a 3D Bessel process, and the right-hand side remains the Brownian motion. Is it 2B is equal to B minus R. So this is the difference that happens on geodesic. Usually your distance profile look like square root 2 times Brownian motion. But if you center around a geodesic, it starts looking like a Brownian motion minus an independent Bessel process. And so I have not told you how to use this in the upper bound, but there's some integrability where you can actually track how this change affects the estimates. And yeah, when you do that, you actually get the correct exponent. So I won't actually go into that because there's not much time left and it's a bit complicated, but yeah, I think this is it.
But it's more about like doing analyzing this process, right? And all these things.
Exactly.
Is
So
that what you're-
there's some estimate which appears, it's like Brownian motion, Bessel process there, and I have to compute its
So R is
probability.
just basically, as you say, like this the empty minus BT. This is just a reflected Brownian motion, right? Around that, the maximum point, or what? Isn't it? Or
For the Bessel processing,
yeah. So So R is
around its maximum, Brownian motion looks like a negative Bessel. Yeah.
exactly.
Hmm.
That's fine.
There's some
Great.
estimates which I have to do, and I have to track how this goes. But this is the core ingredient which goes in. Yeah.
Okay. That's okay. Great. I think let's first thank Manan for this wonderful talk. And any questions?
So I have a question. Sorry. So you mentioned this exponential weights in last passage percolation has some closed form expressions. Are there other examples where you have different distributions and still have closed form expressions?
Yeah, there are some examples, but they're all quite related. So there's exponential weights, and then there are geometric weights, and then there's another model which is this Poissonian last passage percolation, where you instead throw Poisson points on the plane and you do last passage there. But yeah, I don't think there are any other examples actually. So there are just maybe 3 examples. And for anything else, even a little perturbation of this, you basically don't know anything, right?
I see. So there's nothing involving, for example, the eigenvalues of a GOE or something like.
No. The connection for exponential last passage percolation, it actually there's correspondence, the RSK correspondence. If you do that, then you do get connections to eigenvalues of a GOE.
No,
that
but
is true.
The weights are not like spectral gaps in, for example, minor process of GOE.
No, I think yeah, the minor process of GOE it does come up in Brownian last passage percolation. So sorry, there's another model, Brownian last passage percolation. So instead of 3, there are 4 models. But I don't quite remember how exactly it comes up. But you are right that it does show up there also. Yeah.
I see. Okay. So do you know any reference for this?
I think you should be able to find all these integrability references for this in this survey paper by Shishendu. He has a survey paper.
Okay.
He surveys all the known things. So
I think this AMS notice article, right? I think.
Yeah.
Okay. Thank you very much.
Okay. So in case there are no other questions, let's thank Manan again for this wonderful talk, making time today, early morning, to give this talk. Thanks a lot, Manan. Probably sometime actually we will be able to catch you here in person.
Yeah, that would be great.
Yeah. Okay, great. Okay, thank you, and see you all probably next week. Bye, Manan.
Thanks.
Have a good day. Have a good rest
You
of
too.
the day. Yeah.
Bye.
Bye.